Hello and welcome to this MCMA webinar, Rare Earth Materials Update. My name is Joanna Keel and I'm the Manager of Marketing and Membership for the MCMA. I will be serving as your moderator today. Attendees that have joined this webinar has joined in listen-only mode, which means that you are muted. If you do have a question during this webinar, please submit them in the questions pane of your webinar screen. We will answer all questions via email after this webinar has concluded. This webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to introduce our presenter for today's webinar, Kristen Wolotsky. Kristen is a contributing editor for Motion Control Online and has written about motion control and automation for more than 7 years. As a technical writer, she covers a variety of subjects ranging from memory and microelectronics to nanotechnology to lasers and photonics. She previously worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Kristen holds a Bachelor of Science in Physics and a Master's in Optics and Photonics from the University of Central Florida. And now I'd like to hand it over to Kristen to get started.
All right. Thanks, Joanna. Appreciate the introduction, and thanks to the MCMA and everybody who's checking in out there. Yeah, let's take a look at what's going on in the rare earth market. It's kind of an important technology from the standpoint of motion control. Hold on, we're trying to figure out how to get our AV working here. From the standpoint of motion control, in that it's enabled the development of really, really light, really powerful motors that have revolutionized the industry. I don't think that's an exaggeration to say, but anybody who's been following the industry in the last few years knows what's gone on in terms of pricing, and we're all sort of still trying to recover and figure out what the shape of the industry is going forward. And I took a closer look a few weeks back at what's going on in the market and came away with some surprising conclusions. So I'm going to start out just by kind of giving a rundown of the basics of rare earths, bring everybody up to speed, go through the bubble, and then talk about how things started to rationalize and then go far beyond that, and then kind of what you can expect going forward and some tips to think about from a design standpoint. So let's see, magnetic materials. And there is going to be a feature going up on the MCMA website in a day or two that's going to be more about magnetic materials from an end user perspective. So if you're out there specifying or using motors, I've kind of tried to put something together really going into some of the key things you want to keep in mind when you're looking at motors, thinking about materials, pitfalls, things to look for so that you come up with a system that performs the way you're thinking it's going to. But here, let's just kind of go through a snapshot. There are kind of a few key parameters that we really care about. The energy product, that's really a measure of the overall strength of the magnet. The higher the energy product, the greater the field. And from a motor perspective, the more torque you can develop. So the higher the better. And if you'll look, you'll notice neodymium iron boron has a very high MGOE is, or MGO is what people usually call it. Very high MGO, much higher than ferrite or aluminum, nickel, cobalt, alnico. Samarium cobalt is a little bit closer, and we'll talk more about samarium shortly. But that's where people really got excited about neodymium, was when they were able to get this really high energy product. So all of a sudden, things that used to weigh a ton came out very, very light and still lots of torque. On a personal level, I've got a fan that I bought during grad school that you have to lift with 2 hands because of the motor, and one that I bought a couple years ago you can lift with a finger, and it's just an example of that on a commercial level, but obviously it's had big developments on the industrial side of things. So back to magnet characteristics, coercive force or coercivity, that is a key characteristic. That's the amount of field that's required to demagnetize a magnet. And that's obviously, if you've got a magnet that won't stay magnetized, it's not going to do you a whole lot of good. We'll be talking more about that later. And then remanence is the measure of the material's ability to hold on to a field once it's been magnetized. So ideally, you want a material that's got very high levels of all of those. Now, oops, I am just, there we go. So as far as rare earth elements go, you can split them into light and heavy rare earths. The ones that we really care about here, we'll be talking more about, neodymium, obviously, dysprosium, which is used in trace amounts in neodymium iron boron magnets to confer valuable properties. Praseodymium is really something that's found in concert with neodymium. Samarium, as you've seen, is another magnet material. Terbium is another material that can be used to increase coercivity, but it's not used as commonly as dysprosium. Now, the key thing to keep in mind with rare earth elements, despite the name, they're not actually rare. If you take a look at this plot in terms of crustal abundance, they are more common than a number of industrial elements. They're more common than silver, they're more common than gold. So the issue, the reason they get the name is that they are not easy to go ahead and get out of the ground. You don't, with gold or a lot of useful metals, you find them either in very easy oxides or you find them in pure deposits. Rare earth elements, most of the time you find them all clumped together. And that means that it involves a high degree of processing. In many cases, they're also involved with radioactive materials. That means you're grinding, you're filtering, you're washing them. It generates a lot of salty water. You can get radioactive water. Just massive amounts. There are pictures of an area in China where they do a lot of the processing of their rare earth elements up in outer Mongolia, and it's just flooding out of these giant pipes. So there's a lot of effort that goes involved in this, and that's more where it got the name, and that's where the concern is. So taking a look at how this all kind of came together as far as rare earth magnets go, and keep in mind, usually when you hear rare earth magnets, people think automatically neodymium, but samarium is rare earth material as well. It's a light rare earth. So samarium cobalt magnets, likewise, are rare earth magnets. Cobalt brings better properties to samarium. It also helps stabilize it. And samarium is actually not as expensive, anywhere near as expensive as neodymium. The downside with samarium cobalt magnets is they are more expensive than neodymium iron boron magnets because of the cobalt. And it's kind of a question of whether cobalt is going through a price spike as to how expensive they are. So people were pretty excited about neodymium iron boron magnets when they were first noodling around with them. But the problem was they had great energy product, but the coercivity was so-so at room temperature, and the real problem happened when you started bumping up the temperature, because in the absence of any other elements, neodymium iron boron is only good to about 70 or 80 degrees centigrade. It can't really resist demagnetization much higher than that. But in the 80s, people started fiddling around. They started adding dysprosium, which vastly increased the operating temperature range. So you can really work with it now up to about 180 degrees C. They also developed different forms. There's a bonded form that's isotropic, so you can really do a variety of pole definitions. In particular, you can do very high pole counts with bonded form centered, and the downside though with bonded form is your energy product goes down to more like 10 MGO as opposed to the 55 or whatever. And I should mention, by the way, in that table we were just looking at, those are purely representative samples. Just by tweaking the various proportions of these compounds, you're going to make a big change in the properties. So it's just to kind of give you some relative weighting on that data plot you just saw. The article is going to be posting has a lot more detail about some of the different types of magnets, and you'll be able to get a better fix for some of those quantities there. Anyway, back to the centered form. The centered form has the advantage that it's formed under an applied magnetic field. So you wind up compressing it, you get a much better energy product, about 4 times as high as a bonded form, but it is anisotropic, so there's only so much you can do to define poles and so on. Downside of neodymium magnets is that they are vulnerable to corrosion. You've got to coat them. You've got to make sure that coating does not get damaged, or they will start to degrade and your properties are going to go downhill. So anyway, 80s and 90s, there was much more work done to improve the quality of neodymium magnets. And ultimately, we got to the very high quality materials that we're working with today. And if you do a hunt online at some point, there are reams and reams of different grades of neodymium magnets out there. And then you've got your magnet. It's about 30% neodymium by weight, and you just need a few percent of your dysprosium to go ahead and vastly broaden the temperature range. Now, the higher the temperature, the greater the amount of dysprosium you need. So yay, you could use neodymium magnets for high temperature applications, but on the downside, it does increase costs, and you'll see some cost stuff coming up, and it's quite a bit more. It's several times more expensive than neodymium. It also reduces the remnants of the neodymium iron boron, but another key thing is it makes the material more brittle. Now these magnets we're talking about, pretty much all of them are brittle to a point. And it's something where you don't even want to knock them together, kind of thing. They can shatter, they can be very dangerous to handle. So anything that's going to make it more brittle is dangerous and something you just kind of want to keep an eye on, make sure that you're not specifying a motor that's at a higher temperature range than you really need just because that's kind of what you're used to doing and you're just going to throw it out there. You really want to, for a variety of reasons, focus on only getting the performance level that's required. So as far as the kind of lead up to the bubble, there was a time, even coming into the 80s, where there were a number of sources worldwide. And one of them was Mountain Pass mine out in California, which had some pretty high quality grades. Now the problem that they had is when we were talking about how you get the rare earths purified and so on, you wind up with a lot of toxic waste that you've got to deal with. In that area in China I was talking about, there is a massive, like 2-kilometer tailing pond of all the byproducts. So it really is something where you've got to have all of this material and then figure out something to do with it. So they wound up shutting down Mountain Pass as a result of EPA regulations. Now the Chinese mining operations, among other things, the rare earth elements were found as byproducts of other mining operations. So economically, it was a little easier to deal with, slightly less quality, but in terms of the deposits, but there were economies of scale because they were bringing it out with a lot of other stuff. The other thing that was going on over in China is a lot of wildcatting. So there was an analyst I was talking with at one point, actually no, it was a magnet guy, at one point who told me about hearing that a wildcatter at one point had been given a bucket of acid and told, throw it on that hillside and dig up the ore that you can break loose after it sits there for a while. So not necessarily highly focused on the environmental regulations, which means you get a lot of material, you get it cheap. So a lot of price pressure started getting applied, and facilities like Mountain Pass and others around the world shut down. In the meantime, the industry was quite happy to have an opportunity for the lower cost magnets and neomagnets and motors started going into really broad use. And if you take a look, the way it started moving is pretty much sole production wound up going down to China. I think the figure I heard at one point was something like 95 plus. And then the rest of the world just received their materials from there. Now, what started all of the craziness happening in 2011 was China cut its export quotas in 2010. Now, there's a little bit of background here in that there was prior to that, a situation that developed between Japan and China where China cut off rare earth shipments to Japan. That was a result of a political situation, and it doesn't appear, and nobody I've talked to has ever indicated that it had anything to do with the export quotas per se. It was really, had completely to do with territory disputes and so on. But what happened in 2010 when China cut the quotas, everybody freaked out and started saying, oh my gosh, I'm not going to be able to get the materials I need. And certainly if you're trying to supply a broad customer base, you need to know that you're going to have motors to support your production going forward. Everybody figured, hey, we'll double up, we'll get extra, we're going to have a cushion. And that started driving up pricing. And one of the analysts I talked to said, some of the suppliers were picking pricing out of the air because they knew they weren't going to be able to come up with the volumes people needed. But they, went ahead and threw the prices out just, for the sake of, and it turned into this huge bubble. And meanwhile, you had speculators out there who were trying to get material and hoard it. You had the wildcat miners kind of mixing things around, and as probably many of you have experienced, the pricing was changing at one point on a day-by-day basis. There were companies that were doing 15 and 25% surcharges on their motors. I talked to one company where they were told, you have to pay up front the day you order it for your magnets. I mean, it really got crazy. But here is the interesting thing to take a look at. If you look at the table here, you'll see that as far as the quotas go, even when the quota dropped, and it did drop significantly from 2009 to 2010, they never shipped everything that was late in the quota. This was really an artificial bubble, which sort of makes it all the more criminal. So the what is it? Necessity is the mother of invention. And one of the things that started to happen immediately is people were under price pressure and they started looking for ways to get around it. I was talking earlier about, hey, don't pick the high temperature motor unless you really need it. And in a lot of cases, people were taking a look at their requirements and trying to figure out, do I really need this or can I get by with something less? If I need Neo, can I get by with something that's a lower grade? There's an article on the MCMA website about some of the different design approaches, but you can design motors as magnet-centric or copper-centric. So if you go to a more copper-centric design, yeah, it's going to be a little heavier, but if you can get away with it, then you can go with it. I mean, the sense I get talking with integrators and certainly vendors is a lot of people were using neodymium magnets and neodymium motors because they could. They figure, why not? It's easy, it's cheap, it fits the budget. Let's go ahead and do it. So when they had to take a good hard look at what was going on, then they started stepping back. And again, less dysprosium, avoiding it altogether if you can. There's the option to go to Alnico, go to ferrite. So, by the way, I was amused at one point when I was roaming around doing some backup research for this webcast that in one place I saw Alnico listed as a rare earth motor. Cobalt is a rare metal. It's not a rare earth material. So Alnico is not a rare earth magnet. But the other interesting thing that started happening with alternative design is the whole thing of moving into switched reluctance and some of the designs that get away from magnets completely and still for certain applications deliver sufficient performance. So kind of the best of engineering innovations started coming into play. And around that time, as the demand started loosening, the speculators started going, I got a warehouse full of this stuff, and now it's looking like maybe it's not going to put my kids through college. So they started selling off. We had a high peak about August of 2011, and things started to drift down. And by December, they had gone down quite a bit more. And just as a snapshot here, as a snapshot, you can take a look again to the are they rare, are they not rare. We still got very significant supplies of the key rare earth materials. And if you look at these plots, you can also see that the different kinds of oxides and how everything's bound together. And in deposits, you're going to have multiples of these available simultaneously, which is why you have to go through all of the purification steps. But point being that that's not sort of driving the pressure here. So now let's take a look and see where things actually are today. This is one plot for neodymium. There's another that I didn't include that's a neodymium praseodymium oxide. But I thought it was more noteworthy to just sort of see the overall form of the plot. And you can see our little spike there, and it's gone down, down, down. Now, the interesting thing to me is in the run-up to doing the article on this topic and also prepping for the webcast, I heard a lot about, oh my God, the sky's falling, the prices are so low, they're rock bottom. But if you take a look over on the right, they're actually a little higher than they were in 2010. So there's still been some natural market growth. It may not be economically sustainable for the supply chain, but we're not something where we've driven absolutely below where we ever were. Dysprosium. Now here's the thing when I was talking earlier about prices. Take a look at the pricing between, it's actually an order of magnitude between neodymium and dysprosium. So cutting your dysprosium amount even a little bit can really swing the price. By the way, for those who don't know, the legend up there, that just has to do with import-export regulations, whether the material is delivered or whether it's picked up at the suppliers. Nothing that has any bearing on the conversation here. And for later conversation, we can also take a look at Samarium, which is definitely cheaper than this Neodymium, as you can see. And it too has come back down. So what is acting to make all these changes? Obviously, we got rid of the speculation bubble, yay. But there have been a few other things going on. 2011, the World Trade Organization considered the case of China with the rare earth materials and put forth a ruling that they had to eliminate export quotas and tariffs on these supplies, and China immediately appealed. 2014, that was upheld. So if they wanted to stay in the WTO, they had to behave. So at this point, if you're trying to figure out whether it's safe to go back in the water, although most people already have, at least the trigger for the original panic is going to be out of the way. So that's good news. Interestingly, China tried to set up a replacement tax that they figured would help compensate for the loss of the tariff. The analysts that I spoke with for this said it really hasn't impacted the price. There was still just like a step function jump down in pricing. So that's been really fortuitous for customers, certainly. And then there are some other factors at work right now. Part of the problem is there is a lot of material stockpiled just in the legal concerns. And there at one point were dozens of companies out there legally mining in China. But the problem is the licensed producers, centralized economy, they had quotas. And when the market started to slow down demand-wise, they didn't have the option of cutting operations. They still had to meet their quotas. So that's part of the problem. The other part is, as we've discussed, your rare earth materials are co-located. So if you need to get cerium to supply rubbing the faceplates for iPhones and things like that, you are also maybe going to come up with other materials such as neodymium. Even though you don't want to, it's all going to come out together. So that kind of has an effect on that. And then you've got the wildcat operations. And the wildcat mining represents a huge amount of the volume. They have been really trying to do something about it, but it's very hard to control. So that's also had an effect on suppressing pricing. And it's had an effect on the players in the market. Now, one of the companies that stepped in, because the thing that's important to keep in mind about the bubble is all of a sudden the pricing situation became much more rational for some of the other companies that didn't have the kind of economies of scale that China enjoyed in their production. So, for example, Molycorp reopened operations because suddenly they found a way that they could be profitable. Or at least that was the expectation. There was an Australian mining company called Lynas, and they've got Mount Weld mine. Things were reasonable back in the day when I last gave this webcast. I believe it was 2013, and they were, coming on to production. They were predicting, big things, and unfortunately, with the market tanking, they've seen their last quarterly financial. They saw a 19% drop in prices quarter over quarter. Again, the illegal mining they think is a huge factor, and this is a number that I can't confirm independently, but their quarterly financials say that it's about half of China's rare earth production, which is pretty big. Molycorp, unfortunately, in part because of the amount of investment they had to make for remediation before they could even start, I believe they had issues with thorium, water that they had to clean up. But once and at one point they were actually starting to produce product, but again, not able to make it profitable, especially now that the prices are dumping. So they declared bankruptcy last summer, and they've put the Mountain Pass mine and care and maintenance basically put it on ice until such a time as things might become viable again. And it's not just the alternative mines. Actually, producers even in China are hurting right now. There's a big Chinese Rare Earth Association that meets every summer, and then their last summer's meeting, the deputy director of the organization in his speech said, you know what, 90% of the producers have been losing money in the last year. That's pretty big stuff. Elsewhere, I was talking with an engineer who spends a lot of time dealing with suppliers over in China, and he's actually over there. He says the biggest magnet manufacturers that he knows, they got 6 to 12 months of inventory, and they're not seeing strong demand. Somebody else told me that they had, they've talked with companies that have 50% overcapacity right now. So it's getting tough over there. But do remember those prices that we showed earlier. The pricing is still a little bit up from where it was pre-bubble. The thing to keep in mind is what goes up must come down. What goes down must come back up. As we talked about, the bubble was an artifact, but that said, we've gone from sole supplier to having some alternatives, and things are going back to sole supplier. And that means a certain degree of vulnerability. So for those of you out there designing with motors and magnets and so on, might keep in mind, keep your options open. We'll talk a little bit more about that later, but try to not make yourself a one-trick pony where you will be vulnerable if things do go off the rails again. Wow, mixing metaphors with the best of them. Don't try this at home. I am a professional. So what is China doing to stabilize things? For starters, they are making a big effort to curtail illegal mining. Some of the numbers thrown out by their director of the Rare Earth Department were that they'd shut down 67 operations over the course of about 9 months, confiscated almost $345 million worth of product. That said, from what I'm told, that represents a drop in the bucket. So the question is how effectively they're going to be able to go after that, but they're certainly doing their best. But the other key thing that's going on is they've made a move to consolidate licensed operations. So instead of being a gaggle of different companies, they brought them all together into 6 groups. And that way they're going to be able to be much tighter, much more focused on kind of keeping track of who's producing what. I'm told that at least one of the groups has already ceased production temporarily, so there are efforts underway to tighten supplies. So as we were talking about, there are things underfoot. Part of the issue with facilities like Mountain Weld and Mountain Pass, it's not the economics of getting the material out of the ground, it's finding a way to separate it that can meet environmental regulations without being cost prohibitive. And so people are working on some different technologies to try to make that happen in an effective way. Another thing that you can do, though, is think about alternatives. I was talking with a guy named Stan Trout, who was with Molycorp back during the bubble, and one of the comments he made was he would get a lot of calls from people talking to him about, during the bubble, oh my God, magnet prices have gone through the roof. And he started asking them, what are you working with? Well, Centered Neo. And would ask them if they had maybe done a complementary design with Samarium Cobalt. Now, as we've discussed, Samarium Cobalt can be more expensive, not the Samarium part, but the Cobalt. It kind of depends on what's spiking at any given time. But if you're doing a design and you can build it to be compatible with both, then you're future-proofed a little bit so that you're able to be flexible if you do wind up with a spike in one or the other material system. So these are kind of some things to keep in mind. But that is one of the things that came through. No, we're not likely to have another one of these sort of speculation-based bubbles, but there still is a likelihood that things are going to rise somewhat. And anytime you get a constrained supply chain, you're always at risk. So smart designers and machine builders are going to be looking at kind of planning ahead on all this stuff. One of the most knowledgeable people I know in this area, Gareth Hatch, Technology Metals Research, thanks to him for the data plots and the pricing charts and so on. If you're looking for more information in this area, he's a good one to go to. And in summary, so we talked about the bubble and what happened after. We talked about the WTO ruling, which again is going to give at least some underlying stability, but keep in mind China is working to address the oversupply and make sure you're planning for the future.
Great. Thank you, Kristen, for that informative webinar. And thanks for all of our participants today. We did get some great questions that have come in. So if you did have questions for Kristen, please feel free to put them into your questions panel. We will follow up with those questions after this webinar has concluded. I also want to remind everyone that we have recorded this webinar, and an email with the link to the recording will be sent to you within the next 24 hours. And as always, you can be sure to visit www.motioncontrolonline.org for a list of all of our upcoming webinars. Thank you, everyone, and have a great rest of your day.